Hello everyone, welcome to Lecture-2. So this is the second lecture of this lecture series on fundamentals of structural analysis. So in this lecture we are going to understand degrees of freedom, and by understanding the degrees of freedom, how you can define different supports for a structural system. Okay, so let's get started. So first of all, to understand the degrees of freedom, if you want to define degrees of freedom, so you can say that the number of independent coordinates required to define the motion or to specify the configuration of a system, we call it as that number of independent coordinates is actually the degree of freedom of that particular system. So this is like the theoretical language that that we can say, but what it is actually, to understand this, let me draw a diagram. Suppose we have here two coordinates, here x, suppose this is x and this is y, correct? This is x and this is y, and suppose we have this vertical you can say axis also, which is z. So z vertical, I should say, suppose. But now we are only talking about this plane, which is this xy plane. So if we say that this is the 2D plane, which is basically xy plane, correct? Xy plane. Now what I have done, suppose this is the top of your table, right? Just the surface of your table. Now what you have done, you have kept a paper here. Suppose you have kept a paper here. Okay, so this paper or the sheet of paper which you have kept on the table. Okay, so we have considered this, the tabletop, as a 2D plane which is in the xy plane, correct? So this paper is now your system. Okay, this paper is now your system. Now if you want to define the motion of this paper, okay, keeping the paper in touch with your, you can say 2D plane, or you can say your tabletop, how you can, in which directions you can move this. So you can say, you can easily understand that now we can move this paper, this whole system, along this x direction, right? So we can say we can translate, or translation along x direction, right? We can move this paper along this direction also, right? So you can say translation along y direction, correct? So these are the two independent directions. Okay, degrees of freedom, what I said, that independent coordinates, you can say that I can move it along this direction also, I can move it along this direction also, yes. But when you are moving this paper along this direction, okay, you do not only need x, or you do not only need y, you need x and y both coordinates to define the movement of this, you can say define the motion of this particular system, correct? So that's why when we say independent coordinates, so in this case either x or either y, right? Or what you can do, this paper can rotate also, right? This paper can also rotate like this. The paper, suppose it is the same place, it is not translated along x or y, but it is rotating. So you can say here, so this is, you can say, if I can say this is my rotation about z axis, correct? I should cite rotation about z, correct? So these three movements of this particular paper or this system is independent. When you say rotation about z axis, you do not need x or y. Okay, so this is independent. When you say translation along x, it doesn't require z or y, so we can say it is also an independent coordinate. Independent And when you are saying the translation along y, that also doesn't require z or x, so we can say this is also my independent, like while we are defining the configuration of the system, we can independently define only with y. But in these directions, okay, these directions are not independent. These are not independent. Okay, similarly this one, okay, not independent, I can say, right? Not independent. So how many independent coordinates we have to define the motion of this particular system or configuration of this particular system? So you can say we have here, when we are talking about a 2D plane, okay, so we can say there is 1, 2 and 3 independent coordinates to define the motion of this system or the configuration of this, specify the configuration of the system. So degrees of freedom is nothing but the independent coordinates which is required to define the motion of a system on a plane or in a 3D space. Okay, I mean, suppose you have this paper, how many directions it can move, okay, but it should be defined with an independent coordinate. Okay, that's why, like, you can move in any direction, right, on this plane, but when you can define it only with one coordinate, then you can say this is 1 degree of freedom. So for this particular system on a 2D plane, xy plane, okay, we can say it has 3 degrees, it has 3 degrees of freedom. Okay, so it can freely move in 3 independent directions, I mean 1 rotation and 2 translation, okay, independently, right? So it has 3 degrees of freedom. So that is what degrees of freedom is. Okay, I have defined. Now let us go with a 3-dimensional plane. So suppose we have again x, y and z. So suppose z, x and y, z, x and y. Okay, now let us put a box here. Let us put a box here. Okay, so I have a box here, suppose. I have a box here, correct? Now if you want to define the movement or define the you can say system configuration of this particular system, this is also a system, correct? So how will be defining it? In which directions you can move it freely? If you see here, like this 2D space, I can move it along x, I can move it along y, I can move it now along z or z also, because now it is not a 2D space, it is a 3-dimensional space, right? So I can write it here, it is a 3D space, okay, defined by x, y and z. This is also defined by x, y and z, but there we were not allowed to go up. Okay, we were not allowed to go up because we were in a 2D plane. Now we are in a 3D space, so we can move along this direction. So these 3 are my translations. This is also translation. This is also translation. So if I say in a 3D space, if I see this system, if I want to define the degrees of freedom of this system, so I have 3 translational degrees of freedom, we can say DOF, okay, degrees of freedom in this case. Now if you see this particular system can rotate about this y-axis, so it can rotate like this, right? It can rotate like this about the x-axis, or it can rotate like this about the z axis or z axis. Correct? So now we also have three rotational degrees of freedom. In our 2D plane, we had only one rotational degrees of freedom, right, which is rotation about z or z. Now it can rotate about y, it can rotate about x, or it can rotate about z, right? So we have three rotational degrees of freedom in this case, right? So now in total, how many degrees of freedom we have? We can define independently. Like if we see rotation about y, we do not need x and z, right? If we say rotation about z, we do not need x and y, right? So like three independent you can say degrees of freedoms, both in case of translation and rotation. Correct? So we can say this is like rotation about this is y-axis, this is my rotation about z-axis, and this is like rotation about x-axis. Correct? So we have three translational degrees of freedom, means in three direction it can move independently, right? And in three rotational degrees of freedom. So total we have 6 degrees of freedom for this system, right? 6 degrees of freedom for this system, which is in a 3D space. So now if you understand the degrees of freedom, like how it can move freely, in which directions it can move freely, right? So if you understand the degrees of freedom, now we can define the supports basically. How we can define the support? Suppose we have a line element made up of, a line element, right? And we have two joints here, joint A and joint B, like point A and point B, I should say, right? And this is suppose on this ground, now if there is nothing to you can say resist this particular element on the ground, so if you give a force from this direction, okay, if you push it from this direction, it will fall down, right? Correct? Again suppose there is nothing in here, there is no ground itself, there is nothing to support it, right? So what will happen? It will not be stand here, right? It will keep going down like this in this direction also. So when we are saying that we have provided a ground here, so what does it mean? That we have already restricted the movement of this line, okay, along this direction, along the vertical direction. Okay, this is in 2D space. Okay, remember this is in 2D space. I am saying suppose x and y. So we have already restricted the movement of this you can say line along the y direction. So you can say it is the restriction, or I should say constraint along y. Correct? Okay. Now we have another you can say axis also, which is like this, vertical to the perpendicular to the, you can say, our screen. So you can say suppose this is z, which is perpendicular to the screen, remember? Okay, but as we are talking about 2D space, so translation can happen only in x and y. Okay, but it can rotate about z, like our 2D example here. So now if you see, when we have given a ground, we have already restricted the movement of this line along this direction. But again, when we are pushing it in the horizontal direction along x direction, then it will fall down, right? It will fall down. So why it will fall down? Because when we are pushing it with a force F, there is a rotation happening here. Right? There is a rotation happening here. So this is like due to the F. due to the, or I should say, rotation due to F force. Correct? Okay. And again, if I should say, if you are pushing it with F, it will also try to move in along this direction. It will also try to move along this direction. So that means it is not a stable structure. It is not a stable element, because when you are giving a force on the structure, it is not able to stand still. So it is not stable. So this is like sliding due to F. So it is trying, it will be rotating, it is sliding. So it is not stable. It will fall down, right? So now if you want to restrict this movement, suppose I'll be saying that I'll be restricting the movement of this particular point, okay, so this rotation is restricted, okay, this sliding is restricted. So what we are saying actually, that its translational degree of freedom along X, okay, so I should say translational DOF along X restricted, right? Its rotation about Z, so I should say rotational degree of freedom about Z is restricted, okay. And when we say the sliding is restricted, that means the vertical movement is restricted, that means I should say translational degree of freedom along Y is restricted. Okay, when I say translational degree of freedom along Y is restricted, that means it cannot go up also, okay, and it cannot go down also, correct? So that means now if you try to push this point A, this point B will not move, the top part will move, because now for this top part A, you have already have this degree of freedom X, I mean it is allowed to move along X, right, in the 2D space, right? So it will move, but this point B will not rotate, it will not translate along X, it will not translate along Y, okay. So this joint or this node or this condition with restriction for degrees of freedom, we call this as fixed support. So this support condition, okay, this support condition we call it as fixed support, where all degrees of freedoms are restricted. So degree of freedom equal to 0, okay. Degree of freedom is 0 for this point B, correct? So in this case we call it as fixed support. Suppose now if we say that we have this beam, or you can say the line element, and we have the node A and B, it is restricted to, you can say, go in the opposite direction, I mean along Y direction, so I should say, right, X and Y. So this is restricted, okay. It is restricted to move along X direction, so this is restricted, okay, but it is allowed to rotate, this is allowed to rotate, so I should say rotation allowed. If I say at this point, if I apply a force, this will not translate along B, this will not translate along RY, but this will rotate like this, Okay, this will rotate like this. So in this case, what we are saying that we are not, or I should say we are allowing rotational degree of freedom about our this perpendicular axis, which is z axis, about z. So what is the degree of freedom of this particular joint B? So it is only one, right? Because we have only one, I can say about only one axis it can rotate, or one degree of freedom is allowed, right? So if you want to define the, you can say uh, 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 configuration of this particular point, you can say that it is allowed to move, or you can see if you want to allow the motion of this, define the motion of this particular joint, you can say that's about this joint, this line is allowed to only rotate about this joint, correct? So only 1 degree of freedom is allowed, I mean 1 degree of freedom is there, others are restricted, correct? So this kind of condition when we have, we call this as pinned condition. Pinned condition. I am talking about in a 2D space. In 3D space also it is the same. Only rotation is allowed. No translation is allowed in the any direction, right? So we say that only rotation allowed. So you call this as pin support. Likewise, you can create different support conditions where your structure will be stable. Now you see this structure is still not stable, because when you are pushing it with a force, it is falling down because you have allowed the rotation. But suppose you have similar kind of structure here like this. Okay, this structure again, it is not, you can say it is not, what should I say, it is not stable, because this is pinned. Suppose this is pinned, suppose this is only pinned, okay, like this. So this is also because here, if these joints are, you can say the degree of this freedom of this particular joint are, I mean it can translate, it can rotate also, then this particular structure is not allowed. But if you say here, rotation equal to 0, if you say here the rotation equal to 0, then the structure is, even though it is a pinned point, it is stable. We will come to this point again. Okay, this particular things we will try to understand later. Okay, when we'll be understanding the determination in indeterminate structures. So that is different. For now, what I want to say that when you are saying support, so supports we provide to make a structural element or structural system stable. When you say a single element, maybe this single element is not stable with the pinned condition, so you need to go for a fixed condition where this single element is stable when you are applying a lateral force. But when you create a whole system with different, or you can say a configuration of system, configuration of elements, or assembling different kind of elements together, so in that case maybe the conditions, the support conditions will be different. So the main aim to provide the support is to make the structural system or make the structural element stable, right? So now it always depend on your requirement. Okay, it always depending on your requirement, how you will be I can say supporting the structural element. Suppose I just want to support the structure along to move along vertical direction. I do not want this line to move along vertical direction. All other direction, if it is moving, that's fine for me. It is unstable, that's fine for me. So in this case I will have 2 degrees of freedom, because 1 degree of freedom will be restricted, right? Or one movement will be restricted. So like this, by degrees of freedom of a joint or of a whole structural element or system, you can define the supports. Okay, when you are saying a support will be assigning to a particular joint only, not to the whole structure, like, okay, so we'll be assigning the supports in different joints, but this will be a particular point. Okay, but degrees of freedom, when we are saying, it can be for a joint, a single joint, or it can be for a whole system as well, right? So I hope it is clear to you what are what is degrees of freedom, and how we can define the supports by understanding by our understanding of degrees of freedom. Okay, now there are different other supports also. This is pinned, fixed. Now suppose you have suppose, what should I say, you have a line like this, sorry, this, you have a line like this and a system like this. Okay, and what you are doing, you are saying that I'm allowing this point to move along this direction. Okay, but I am restricting this joint to move along this direction. It cannot move along this direction also, it cannot move along this direction. So here this is allowed, this is restricted, restricted, restricted. Even suppose here this rotation also restricted. Okay, this is also restricted. So when you are allowing you can say the joint to translate along any particular direction, then we call it as roller supports. We call these as roller supports, because it can roll along that particular direction. So we have some symbols like pin support like this. Okay, so it is pinned here. Okay, simply you can say it can rotate along this point. We say fixed support like this, that means it cannot rotate, it cannot translate also. We say roller support, so roller support is something like this, you can say it will be translating along this particular direction, right? So there are different such supports you can define as per your requirement, depending on the, or you can say based on the understanding of degrees of freedom, right? So I hope it is clear to all of you what is degrees of freedom and supports. So in our next lecture we will try to understand more about these by defining determinate and indeterminate structures. Okay, so see you in the next lecture. Thank you.